Hello everyone, I'm Azalea Rod and I will be talking to you about our recent work on incorrectness separation logic, or ISL for short. I will show you how we combine two existing techniques, namely separation logic from the correctness world with the incorrectness logic of bug catching world to develop a local compositional bug catching technique for memory safety bugs. I will show you, just like the original separation logic, ISL is local, compositional, and therefore can be scaled to large code bases. And just like the incorrectness logic of Peter or Han, incorrectness separation logic supports under-approximate reasoning and therefore guarantees the absence of false positives. To find out more, please tune in on Thursday, July 23rd at 9:15 PST. See you there.
Hi, our talk is about the following problem. Suppose you've defined linked list segments in the canonical way in separation logic. These are list segments without data values, just next pointers. Now, suppose you have a list segment traversal program that chases those next pointers until you reach the final guard. Let's suppose you'd like to run two versions of this traversal program in parallel with each other. You'd like to give the combined program a simple specification, starting from a list segment from X to Y, and with a list segment from X to Y. The intuitive idea is simple. Take your list segment, divide it into two read-only copies, distribute one read-only copy to both threads, do your traversals, get back two read-only copies after the parallel code, and then recombine two read-only copies into one copy with full access. Unfortunately, although that idea is intuitive, the proof sketch has several unsound leaps of reasoning. We're going to show what the errors are and how to fix them. In brief, we have a fresh approach to verify concurrent programs that use simple data sharing paradigms for read-only resources. We make two technical contributions. First, we use two kinds of separating conjunctions simultaneously, weak to represent sharing and strong to represent disjointness. And we borrow nominal labels in the jump modality from hybrid logic to help smoothly split and combine resources. Hope to see you at the talk.
Hi everyone. In our talk, we will focus on the problem of counting so-called minimal unsatisfiable subsets. The input of our problem is a set of Boolean clauses, or equivalently, a Boolean formula in CNF. For example, assume that we are given these four Boolean clauses that you can see at the bottom of the slide. Clearly, these clauses are unsatisfiable because the first two clauses contradict each other. If we are given an unsatisfiable Boolean formula, we often want to analyze this unsatisfiability. To do so, we can, for example, draw the power set of these clauses so we get this picture. Then we can somehow determine which subsets are satisfiable and which are not, so we get this picture. And now we can see that there are two sources of the unsatisfiability, these two. The sources are called minimal unsatisfiable subsets. Intuitively, the more minimal unsatisfiable subsets there are, the higher is the degree of the unsatisfiability of the formula. In this talk, we will present an algorithm for counting the number of minimal unsatisfiable subsets.
Nonlinear correct interpolant generation. Our goal is to investigate a new efficient and general approach to correct interpolant synthesis for nonlinear arithmetics. The problem of interest is as follows. Given two formulas, phi xy and psi xz, the conjunction is unsatisfiable. How to find a single polynomial hx such that hx greater than 0 is an interpolant for phi and psi? The main contribution of this work consists of the following 4 points. Firstly, we prove the existence of such hx. Secondly, we discuss how to compute such hx by semi-definite programming. Thirdly, we discuss how to avoid unsoundness caused by numeric error, either by verified semi-definite programming solving or posterior symbolic verification. Lastly, we discuss how to apply such a result to invariant generation in program verification.
Hello everybody, my name is Claire Dross. I work at Edacor, a company providing tools for the ADA language. In my team, we develop a tool for formal verification of a subset of ADA named Spark. From the start, the Spark subset has been restricted to prevent aliasing, therefore avoiding the need for a memory model. Support for pointer has been added in recent versions of Spark, using an ownership policy inspired by Rust to enforce non-aliasing. Following this support, we wanted to allow the verification of imperative algorithms over recursive data structures. However, to do that, we had to introduce a restrictive form of aliasing called borrowing. If you want to know how we managed to adapt the verification tool to handle these aliases without introducing a memory model nor extending the first-order logic basis of Spark, please attend our talk.
Hi there. I don't think I need much words to convince you that we are living in a world filled with stochasticity. Just like what I quoted here from Joseph Dube, the name random variable we are familiar with today actually came out of a toss against another terminology called chance variable. For yet another example concerning the current COVID-19 pandemic, the number of infected cases is surely not deterministic, and there are models like stochastic differential equations that are used to model and simulate the evolution of the infection. Well, in my talk, I will show that given a continuous time stochastic system modeled by stochastic differential equations, how to find a tight upper bound on the probability that the system violates a given safety specification over the infinite time horizon. To get a closer look, you are highly welcomed to join the talk.
In this talk, we provide a faster algorithm of bounded value iteration for stochastic games. Bounded value iteration is a technique to approximate reachability probability with precision guarantee. We introduce a global propagation technique which resolves a termination issue due to end components. Existing algorithms require to compute the set of all end components, which can be computationally expensive. In our algorithm, we don't need to do that anymore. In our experiment, we compared our algorithm with 3 variants of the existing algorithm. We observed that our algorithm achieves stably fast computation and the fastest in about 50% of instances, while every other algorithm sometimes suffers long computation time or computation failure.
SDMC is a statistical model checker that uses antithetic and stratified sampling techniques to reduce the number of samples and hence the amount of time required before making a decision. The tool is capable of statistically verifying any black box probabilistic system that Prism can simulate against probabilistic bounds on any property that Prism can evaluate over individual executions of the system. We have evaluated our tool on many examples and compared it with both symbolic and statistical algorithms. When the number of strata is large, our algorithms reduce the number of samples more than 3 times on average. Furthermore, being a statistical model checker makes SDMC able to verify models that are well beyond the reach of current symbolic model checkers. On systems with more than 100 states, SDMC was able to check 100% of benchmarks compared to existing symbolic methods in Prism, which only succeeded on 13% of systems. The tool, installation instructions, benchmarks, and scripts for running those benchmarks are all available online as
a Bloom filter is a standard probabilistic data structure that encodes an approximate set of objects, trading an increased space efficiency for a weaker probabilistic membership test that has a small probability of giving incorrect results. Bloom filters are fairly popular and are used in many modern software tools, such as web caches, content delivery networks, and even your very web browser, collectively reaching over billions of users. Despite this, the prior analyses of this data structure have had a long history of errors, requiring several corrections and corrections of these corrections, leaving little confidence in its true behaviors. Our research tackles this problem, producing a modular framework for proving the probabilistic properties of approximate set data structures, and use it to provide the first machine-checked proof of the properties of a Bloom filter. We also find that these properties are composable, and use the framework to construct entirely novel variants of these data structures that are correct by construction. So how exactly do we do this? Come to my poster session to find out.
In our work realizing omega regular hyperproperties, we are considering the problem of deriving implementations directly out of hyperQPTL specifications, which is a powerful hyperlogic that allows us to express hyperproperties, so properties that relate multiple execution traces to each other, paired with omega regularity, which means that in this case we are also able to quantify our propositions. And especially we're capable of quantifying over a proposition in front of this trace quantifying mechanism of hyper-LTL. And this means that we are also capable of expressing promptness properties and properties like uniform termination. So if you're interested in that, make sure to check out our talk, which is the first talk of the first synthesis session at 9:15 a.m. So see you there.
Hello everyone. In CAV 2020, we will introduce you to our new tool, Amethyst. Amethyst is a tool for automated controller synthesis for stochastic systems. Given a model described by a system of difference equations with stochasticity, disturbance, or noise on the states, Amethyst constructs a Markov decision process to represent the model. Then, given a high-level specification like safety, reachability, or reach avoid, Amethyst computes a formally correct closed-loop controller to satisfy the specification. In Amethyst, the algorithms used to construct the model and to compute the controllers are implemented in parallel. They can run on CPUs, GPUs, or hardware accelerators like FPGAs, which allows for scalability and efficient computation. One application domain Amethyst can serve is probabilistic robotics. It can be used to design certifiable controllers for safety-critical applications, like, for example, designing the collision avoidance system in an autonomous vehicle. Stay tuned and see you in CAV 2020.
Hello, have you ever been impressed by the recent successes of deep learning, especially deep reinforcement learning? Deep neural networks can be trained from scratch to play various challenging games like chess, Go, StarCraft, and many others. What is remarkable here is that the deep learning models don't use any domain-specific heuristics and significantly outperform human experts. Learning to play games are definitely very interesting, but can deep learning make a big difference in other challenging and perhaps even more fundamental domains like program verification? The answer seems positive since there are many interesting similarities here between gameplay and program verification. For instance, the grammar and the checker used in program verification are fairly similar to rules and the environment of games. However, there are also some new challenges to overcome. To learn more about this work, please come to our talk at CAV 2020. Thank you.
Hello, my name is Marcel Vasquez-Chanlate, a PhD candidate at the University of California, Berkeley. Together with my advisor, Sanjit Sesha, I have been working on the theory and tools for communicating formal specifications through demonstrations. In this talk, I will discuss our recent work on inferring specifications from demonstrations using the principle of maximum causal entropy. Our goals for this work are to have a noise-resistant, unsupervised, and Bayesian method for inferring formal specifications from demonstrations. To this effect, our contributions are as follows. First, we formulate a robust inference method using the principle of maximum causal entropy. Compared to our prior work, this method supports stochastic environments. Next, we provide an efficient implementation based on binary decision diagrams. Finally, we provide an experimental validation of this method.
Do you know that feeling when you are correcting exercises of your students and it just doesn't end? Don't you hate it to give the same feedback over and over again? Wouldn't you love to have a way to automate this process? Well, look no further. We present Automata Tutor version 3, which supports so many types of exercises that you want to have in your course on theoretical computer science. And it automatically grades the problems and gives meaningful feedback to the students. To find out more about this amazing tool, view our talk, have a look at our paper, or directly visit us at automatatutor.com.
Hello everyone, I'm Priyanka Gulia, and I'm going to talk about Manthan, a data-driven approach for Boolean function synthesis. This is a joint work with Kuldeep Mil and Shubhajit Roy. So given a relational specification between inputs and output variable, the goal of Boolean function synthesis is to synthesize each output variable in terms of input variable such that the specification is met. To do so, we propose a data-driven based approach called Manthan. Manthan uses machine learning to come up with approximate candidates. And as we all know that machine learning needs data, Manthan does constraint sampling to generate the data. Later, the candidates are repaired using formal and automated reasoning. We compared Manthan over 609 publicly available benchmarks with the state-of-the-art tools C2SYN, VFSS, and CADIT. And the punchline here is the state-of-the-art tools could solve at most 280 instances, whereas Manthan can solve 356. That's an increment of 76 benchmarks over the state-of-the-art. To know more about Manthan, please refer to our paper or 17 minutes long talk. The tool is available open source. Please give it a try. Thank you.